The digital age has ushered in an era of unprecedented data generation. Every click, every transaction, every sensor reading contributes to a massive and ever-growing ocean of data. This phenomenon, aptly termed big data, presents both immense opportunities and significant challenges for businesses and organizations worldwide. Big data is often characterized by its volume, velocity, and variety. The sheer volume of data generated is staggering, reaching exabytes and zettabytes. This data flows in at incredible speeds, requiring real-time processing in many cases. Moreover, data now comes in a variety of formats, from structured databases to unstructured social media posts and sensor data. The implications of big data are profound. Businesses that can effectively harness and analyze this data gain invaluable insights into customer behavior, market trends, and operational efficiency. This translates into a competitive advantage, enabling them to make data-driven decisions, improve products and services, and optimize operations. However, managing and extracting meaningful insights from big data is no easy feat. Traditional data processing tools and techniques often struggle to handle the scale and complexity of these data sets. This is where Hadoop, an open-source framework designed specifically for big data processing, comes into play. Hadoop, named after a toy elephant owned by the creator's son, provides a reliable and scalable infrastructure for storing and processing massive datasets. At its core, Hadoop leverages the power of distributed computing, dividing large data processing tasks into smaller chunks that can be executed in parallel across a cluster of commodity hardware. This distributed approach allows Hadoop to handle petabytes or even exabytes of data with remarkable efficiency. Two key components form the foundation of Hadoop's architecture: the Hadoop Distributed File System, or HDFS, and yet another resource negotiator, or YARN. HDFS provides a fault-tolerant and scalable storage layer, distributing data blocks across multiple nodes in the cluster. This distributed storage ensures data durability and availability, even in the event of hardware failures. YARN, on the other hand, acts as the resource manager and job scheduler for Hadoop. It efficiently allocates resources such as CPU, memory, and network bandwidth to various applications running on the cluster. YARN's dynamic resource allocation capabilities ensure optimal utilization of cluster resources and enable concurrent execution of multiple applications. Hadoop offers a compelling value proposition for organizations grappling with big data challenges. Its distributed architecture provides unparalleled scalability, allowing businesses to handle rapidly growing datasets without compromising performance. The use of commodity hardware further enhances cost-effectiveness, making Hadoop an attractive alternative to expensive proprietary solutions. Moreover, Hadoop's fault tolerance ensures data durability and high availability. With data replicated across multiple nodes, the system can withstand hardware failures without data loss or significant downtime. This resilience is crucial for businesses that rely on continuous data availability for critical operations. However, Hadoop does come with its own set of limitations. One notable drawback is its complexity. Setting up, managing, and optimizing a Hadoop cluster requires specialized skills and expertise. Additionally, Hadoop's batch processing nature may not be suitable for real-time or latency-sensitive applications. Another consideration is Hadoop's storage overhead. HDFS's data replication mechanism, while ensuring fault tolerance, also increases storage requirements. Businesses must carefully evaluate their storage needs and costs when deploying Hadoop. Despite its limitations, Hadoop has gained widespread adoption across various industries. Its ability to process and analyze massive datasets makes it an invaluable tool for a wide range of applications. In the retail industry, Hadoop is used for customer segmentation, targeted advertising, and inventory optimization. By analyzing customer purchase history, browsing patterns, and demographic data, retailers can gain insights into customer preferences and tailor their marketing campaigns accordingly. Financial institutions leverage Hadoop for fraud detection, risk management, and algorithmic trading. By analyzing real-time transaction data, Hadoop-powered systems can identify suspicious patterns and flag potential fraudulent activities. Healthcare providers are turning to Hadoop for genomic research, drug discovery, and patient care management. The ability to process vast amounts of genomic data accelerates research efforts and enables personalized medicine based on individual genetic profiles. Despite its successes, businesses face several challenges when implementing and using Hadoop. One common challenge is the skills gap. Finding experienced Hadoop professionals can be difficult and costly. Another challenge is data integration. Integrating data from disparate sources into Hadoop can be a complex and time-consuming process. Furthermore, ensuring data quality and governance within Hadoop is crucial. With large and diverse datasets, maintaining data accuracy and consistency requires robust data quality management practices. Section 5. Setting up your Hadoop playground. A step-by-step installation guide. To embark on your Hadoop journey, you'll need to set up a Hadoop cluster. This section provides a step-by-step guide to get you started. Step 1. Choose your distribution. Several Hadoop distributions are available, each with its own strengths and weaknesses. Popular choices include Apache Hadoop, Cloudera Distribution Hadoop, also known as CDH, and Hortonworks Data Platform, or HDP. Step 2. Gather your hardware. You'll need a cluster of machines to form your Hadoop cluster. The number of machines will depend on your data size and processing needs. Each machine should meet the minimum hardware requirements for the chosen Hadoop distribution. Step 3. Install an operating system. Install a compatible operating system on each machine in your cluster. Linux distributions such as CentOS and Ubuntu are popular choices for Hadoop deployments. Step 4. Configure network settings. Ensure that all machines in your cluster can communicate with each other over the network. Configure static IP addresses and hostname resolution, either through DNS or the /etc/host file for each node. Step 5. Install Java. Hadoop is written in Java, so you'll need to install a compatible Java Development Kit or JDK on all nodes. Step 6. Install Hadoop. Download the Hadoop distribution of your choice and install it on each node in your cluster. Follow the installation instructions specific to your chosen distribution. Step 7. Configure Hadoop. After installing Hadoop, you'll need to configure various settings. This includes HDF settings, Yarn settings, and Hadoop environment variables. Step 8. Start Hadoop daemons. Once configured, you can start the Hadoop daemons or services on each node. The core daemons include the name node, data node, resource manager, and node manager. Step 9. Verify your cluster. After starting the daemons, verify that your Hadoop cluster is up and running by accessing the Hadoop Web UI or running Hadoop commands. Section 6. Speaking Hadoop Essential Commands for MapReduce. Once your Hadoop cluster is up and running, you can start interacting with it using Hadoop commands. These commands allow you to manage files, run MapReduce jobs, and monitor cluster health. Here are some essential Hadoop commands. 1. Hadoop FS. This command interacts with the Hadoop Distributed File System, or HDFS. Use it to create directories, upload files, download files, and list directory contents. 2. Hadoop jar. This command runs a Java archive, or jar, file containing your MapReduce job. 3. Yarn. This command interacts with yet another resource negotiator, or Yarn, which manages resources and schedules jobs in Hadoop. 4. Hadoop DFSadmin. This command performs administrative tasks on HDFs, such as balancing data across data nodes. 5. Hadoop job. This command manages MapReduce jobs. Understanding these basic Hadoop commands will enable you to interact with your Hadoop cluster, manage files, and run MapReduce jobs effectively. Section 7. Yarn, the orchestrator of Hadoop's power. Yet another resource negotiator, or Yarn, is a pivotal component of the Hadoop ecosystem, responsible for resource management and job scheduling across the cluster. Yarn enhances Hadoop's capabilities by enabling the execution of various data processing frameworks, not just MapReduce. Importance of Yarn. Before Yarn, Hadoop relied on the MapReduce framework for both resource management and data processing. This monolithic architecture limited Hadoop's ability to support other processing models. Yarn decouples resource management from data processing, allowing different processing frameworks like Spark, Hive, and Pig to run alongside MapReduce on the same Hadoop cluster. Usage of Yarn. When you submit a job to a Hadoop cluster running Yarn, the job request goes to the resource manager, Yarn's master daemon. The resource manager negotiates resources with node managers, which manage resources on individual nodes. Once resources are allocated, the application master, a process specific to the submitted job, is launched. The application master manages the job's execution, requesting and releasing resources from node managers as needed. Yarn architecture. Yarn's architecture consists of three main components. 1. Resource manager, the master daemon responsible for managing cluster resources and scheduling applications. 2. Node manager, a daemon running on each node, managing resources like CPU and memory on that node, and reporting resource availability to the resource manager. 3. Application master, a process launched for each submitted application, responsible for negotiating resources with the resource manager, executing the application's tasks, and monitoring their progress. Yarn's flexible architecture and resource management capabilities make it a key enabler for running diverse data processing workloads on Hadoop, supporting the evolving needs of big data analytics. Section 8, your first MapReduce program, a practical demonstration. Let's dive into a practical example of a Hadoop MapReduce program. This program will count the occurrences of each word in a text file. Step 1, the word count program Java import java.io.io exception, import java.util.string tokenizer, import org.apache.hadoop.conf.configuration, import org.apache.hadoop.fs.path, import org.apache.hadoop.io.int-writable, import org.apache.hadoop.io.text, import org.apache.hadoop.mapreduce.job, import org.apache.hadoop.mapreduce.mapper, import org.apache.hadoop.mapreduce.reducer, import org.apache.hadoop.mapreduce.lib.input.file input format, import org.apache.hadoop.mapreduce.lib.output.file output format, public class word count, public static class tokenizer mapper extends mapper private final static int writable 1 equal sign new int writable 1, private text word equal sign new text, public void map object key text value context throws IO exception interrupted exception string tokenizer iter equal sign new string tokenizer value.toString, while iter dot has more tokens, word dot set iter dot next token, context write word 1, public static class int sum reducer extends reducer private int writable result equal sign new int writable, public void reduce text key iterable values context throws IO exception, interrupted exception, int sum equal sign 0, 4, int writable val, values, sum plus equal sign val dot get, result, set sum, context, write, key result, public static void, main string args, throws exception, configuration conf equal sign new configuration, job equal sign job get instance conf word count, job dot set jar by class word count dot class, job dot set mapper class, tokenizer mapper dot class, job.set combiner class, insumReducer.class, job.set reducer class, insumReducer.class, job.set output key class, text.class, job.set output value class, intritable.class, file input format, add input path, job new path args 0, file output format, set output path job new path args 1, system exit job wait for completion true, 0, 1. Step 2, compile and package. Compile the Java code and package it into a jar file, for example. Step 3, run the job. Upload your input text file to HDFS and run the word count job using the command hadoop jar word count.jar input path output path. Replace with the HDFS path to your input file and with the desired output directory. Step 4, view the results. Once the job completes, check the output directory in HDFS for the word count results. Each line in the output file will contain a word and its frequency, separated by a tab. Section 9. Conclusion. Embracing the power of Hadoop. In conclusion, Hadoop has emerged as a transformative force in the realm of big data analytics. Its distributed architecture, fault tolerance, and scalability make it an ideal platform for processing and analyzing massive datasets that were once beyond the reach of traditional data processing techniques. While Hadoop does present challenges in terms of complexity, skills gap, and data integration, its benefits far outweigh its limitations. As businesses continue to grapple with the ever-growing deluge of data, Hadoop provides a robust and cost-effective solution for extracting valuable insights, driving innovation, and gaining a competitive edge. Embracing the power of Hadoop is no longer optional but essential for organizations seeking to thrive in the data-driven world of today and tomorrow.